Okay, so I hope my screen is visible.
Yes, sir.
Hmm. So week 10 all about the debug and test this topic. So debug and profiling and static analysis and testing. These are the topics for the week 11. So mainly topic is the debug actually, debug and testing. How we can debug our code in the microcontroller. So what are the things we follow for that? So, Professor, I've discussed about this. So, first topic is mainly debug is discussed, and so debug means basically if our code have some bug, okay, or bug means some logical error or any error where because of that our code is not working properly and failing at some place. So, how we can debug the error and how we can identify the error? Sometimes in the microcontroller because that code actually runs on the controller hardware, so not on our program that our computer. So once we generally test just generally compile our code in our system, but after that we upload our code into a microcontroller and that code runs on the microcontroller. So, but still, if our code is running on the microcontroller, then how we can debug the code step by step, or how we can check the value at the particular stage in the code. So that is a debugging process, and there are multiple you way to perform the debugging on the code. So one way is just called as a single step debug. Okay, so what is the single step debug? Uh, Basically, we just set some breakpoint. We set some breakpoint in the code, or we stop our code at some particular point. After that, we execute our code step by step, line by line. And during that time we can also check all the we can trace all the variables value, we can trace the registers value, we can trace the memory space, everything we can check. So after executing one line, then we can check what effect is there in the memory registers and variables. So during by this process we can debug our code. Okay, so for sample I have this code. So this is one code, okay, and this code is simply is performing one task, and this is STMQID, okay, and my board is also connected on this my computer. So this is just a register label code, and the task for this code is just a pressing the button and LED will be turned on. Okay, let me show you the connection and working for this. Just I'm opening my camera, so quickly show you. Okay, so you can see this board is connected. This Nucleo board I have, and one LED is connected in this to D8 pin, and black pin is connected. Ground pin is connected to ground pin in microcontroller. Okay, and there is one push button we have in this board. This blue button, and when we press this button, this LED actually turn on, and when we leave it, that LED turn off. Okay, so this is the working for this microcontroller and this our program. Okay, so I have uploaded this program which is all on your screen actually in this microcontroller, and this is working like this. Okay, so I'll just show you how we can debug this. So you can see now this code is simple. We have mentioned one RCC that address. Actually, this is register level code. Okay, so each address is defined, each memory location address is defined. After that, we are setting the value, enabling all these things. So I've already discussed this type of program in the initial session. I'm just recapping this. So what we are doing in this program. So first is this is the clock registers. Okay, so clock registers is RCC registers where we can enable the clock that clock for any part of the microcontroller. So what part actually we are using in this program? We are using port A. Okay, so port A pin we are using for as a that output pin. Okay, so you can see port A output data register. So A and one pin we are using as a output pin for the LED light. Okay, and another port C we are using as a input, that is actually push button. When we are pressing our button, so the one input, this means once a signal will be changed high to low like this. So in that case, we will get some input, and based on that we will turn on our LED. So we are using port C one pin as a input, okay, and port A one pin as a output for LED. So to enable this port A and GPIO, basically these are actually GPIO, general purpose input output, port A and port C. But we have to enable clock for them. So because of that, we are just maintaining all the registers address. So this is clock, RCC clock, which is connect to the bus where all this GPIO actually connected. Okay, but we have to set our port mode. Actually, what mode we want to use for the port A. Okay, so we have this register address for that mode selection. So that means port A pin we want to use as a output pin. Port C pin we want to use as a input pin. And for port A, so we have to set some data to turn on the LED for some particular pin. What pin we are using actually here? So on that pin, we will set our value to high. Okay, high means one value we will set. So our LED will be turned on. Once the value will be make change, so value will be changed to 1 to 0. So LED will be turned off. So that things we are doing. So that means this is GPIO output data register, and we will pass some value at this particular pin. Based on that, LED will be turned on or off. And this is GPIO-C as a input data register. So here we are getting the push button input. Okay. So based on this condition, we will turn on our LED. Now what? So this is just a initialization for the memory address for the each registers which we will use. So first thing what we have to do, RCC enable. We have to enable our clock for port A. Okay. So first bit actually each register have the 32 bit register. Okay. But so RCC enables this register's first bit is actually represent the GPIO A. If you can remember, so that that address we have. Hmm, let me show you. So GPIO, this is the GPIO mode, but we have this one RCC. Okay, so that is uh, GPIO. Yeah, this is RCC. Okay, inside this RCC register, and here we have some memory place. Here also we have to select. 1 second. So inside the RCC registers also we have to move to the AHB1 peripheral register enable clock register. So that is where HV1, not this. Okay, H1, AP1, AP1, HV3, HN. This one. Okay, the peripheral clock enable registers. This is also not, I think. This one. So AHB2, because our GPIO are connected on this AHB2 bus. Okay, and this here you can see all GPIO pins are actually defined. So if we set this pin as a 1, so that means that clock will be enabled for that GPIO. If we make this value as a 0, so that clock will be disabled for this. So GPIO A, port A. Okay, so this is GPIO port A. This is GPIO port B. This is GPIO port C. So if we set our first bit as a 1 and third bit as a 1, so that clock will be enabled for port A and port C. So that things we have done here. So by this value, so we have set our register value for 0 bit and second bit. So this is actually third. Okay, too high. And this is just a debug comment print statement. We will I'll show you how we can use this. And this is GPIO mode. Same things. We will set our register address. We will enable our mode for GPIO A as a output mode. Okay. So that is the some value we need to assign for GPIO mode register as a output. GPIO C actually we have to set as a input mode. So that mode we have configured by this command. After that, what we are doing, we are simply running a while loop. So inside the while loop, so this loop will run continuously. Okay, and we are reading the input from pin 13. So we will check what is the value at this pin 13 we have in the input data register. Okay, so input data register, if the pin number 13 is high, so that means our input signal is high. So based on that, we will turn on our LED. If input signal is low, we will turn off our LED. So we are checking this condition. So we are reading the some particular bit, 13 bit data what we have. So based on that, if this is 0, we will turn on our LED. Okay, so this is the turn. We are just setting 0 value at that pin. Otherwise, we are setting 1 in the output data registers for that LED bit. Okay, so this 9 is actually a LED bit port value. So now this is a one. This is just a code. It is working fine. Okay, and suppose what happen if we want to debug if any error is there. Suppose we miss something like we miss this enabling. Okay, we miss enable to port A. So it will work or not? How? What is the behavior of this? So let's run this code. It will not give any error during the build project. So let's run this. Okay, now it is not giving any error. Okay, but then if we just run this, so when we just upload this on our board. Okay, so let me turn on my ready. So you can see. So now this is already uploaded here, but when we just click on this, so now this is not working. Okay, our LED is not turning on when I'm pressing the button. Okay, so this code is not working. So how we can debug step by step this code? And so for this, so mostly actually in our board we have the debugger circuit also. So that debugger circuit actually interact with the IDE that provide the information at the runtime when our program is running on the microcontroller. But all information will be provided to the IDE, and we can step by step debug our program. So how we will do this? So we will just click on this, and there is button debug as. Okay, so debug as when we click first time you have to configure something. You have to set the configuration. So first here you can see we can select the debugger here. Okay, so debugger, which type of debugger we want to use here. So there are two, SWD and JTAG. Okay, so which is discussed in the Week-11 lecture also. So these are two type of debugger. So here we will use the serial wire debuggers, SWD, and that is by default selected. And first time this enable, we have to click this enable button, serial wire viewer. This is useful if you want to trace the value with the help of some print statement, because that is also a one way to perform the debugging. You can use simple print statement in your code and see what value you are getting by the print statement at particular stage. Okay, so you can enable this. By default this value is coming clock and this port number. You can just use same, and after that just click debug button. Okay, so when we click on the this button, so it will move to the debug mode, and your code will stop at the first line of the main function, because this is the entry point of this code, main function first line. Now here from you can just run your code step by step. There are two options on the top. So that is one is step over and another is step into. So step over means if any function is called from this function, so step over will directly execute that function. It will come out directly. Okay, but step into will enter into the another function also. So the step by step that function step will also be visible. Okay, but so here you can use because we are not calling any function in this, so we can select any here. So step into or step over. So when I click step uh, here, So step that first step into, you can say this is moved. Okay, so this is moved. At the same time, here you can also see the disassembly code for this. Okay, so I think that is not coming. One second. So window and okay, so disassembly, that is not generated. Okay, so let's again move to once more. Okay, this is not generating. Okay, so this is just also a one way to check the code at the assembly language level. So disassembly means one assembly level language code will also be visible on the right side, and you can also see how the actually processor level how the instructions are moving executing on the processor level in the assembly language format, or we can say machine level instructions. But here now we have run this code three steps, so now you can see what value we are getting. So let's move one more. Okay, so now this disassembly is now also visible. Okay, so you can see. So when we click on this, now green, this is the selection on the both sides. So this is our actual code in the C, but corresponding assembly instruction for this. Okay, so this is selected. So that instruction code, then registers, what are the instruction name, registers, that value, all are coming here. So you can also check the machine level instruction debugging here step by step. Otherwise, so once what part you have actually execute. Okay, so what part you have already execute here. If you select any registers, okay, suppose if you check RCC enable, if you just leave the cursor here, you will get all the information of this register. So what is the value at this RCC ENR? Okay, so this RCC ENR value you can see here in the binary format. Okay, so this is 100. What type is there? Binary is this means for this registers we have 32 bit, but only that third bit is set to high. Okay, so here we commented, so this first should also be high, but we missed it, and because of that a clock is not enabled for that. Okay, so we can check registers level value for each that step, what update is happened. And due to this, because we have not enabled the clock for port A. Okay, and here we are updating some value in the port area, this mode register, GPIO mode registers. Okay, what we are updating here, so we are setting this 1 1, that means 0 0 value at 18th location. So because this GPIO a mode registers, if you see this, so this is actually general purpose registers, and this one. Okay, huh. So 18 means ninth pin. Okay, we have to set two value because we want to use this GPIA mode as a output pin. So we have to set our value as a 0 1 here. Okay, so 0 1 value we have to set for ninth pin. Okay, so ninth pin is this. So that means this two value we have to set as a 0 1. Okay, so we will check this operation is happening or not when we are performing this operation. So if you see this, now we have performed this task here. That means, and first thing we reset these two places as a 0. After that we set as a 18 bit as a 1. Okay, so that will become a 0 1. So here means 18 and 19 both will become 0, but then we will set as a 18 as a 1. So 19 is already 0 and 18 is 1. So 0 1 is now set to this registers. But this is happening or not? So let's see this value. What value we have? Okay, so we have this value in the registers. So our value should be updated properly, but it is updated or not. So we will identify it here. So one second. Okay, so you can see this is value we have, and now here you can see what is the place where our value is coming. So this is the 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. Okay. So according to our code, this 2 bit should be become 0, 1. Okay, because we have done our operation 0, 1, but this is not changed by the code. Why this is not changed? Okay, so we have performed this operation, so this should be changed, but this is not changed by the execution. So why this is happening? Because at that part our clock is disabled. Okay, without enabling the clock for any particular part of the hardware. Okay, so that actually hardware not works, that part actually not works any operation. So if we have performed this operation, we try to write something, but that part clock is disabled, so no operation will be performed on that. So we can see here that means something is wrong. We are performing this updation, but that is not happening on the registers, and that value is not reflected in our registers after modifying the value. And same things if you can see this value. Okay, so just move to the next step again. Mhm. So GPIO, now this step is done. And now you can see what value we have. Okay. So this is this one. And what we have done for this, we have done uh, that that means 26. 26 and 27 values should be set as a high. Or this is inverse. Okay, both should be set as a 0. For input mode, value should be 0. Okay, 0 0. So are we getting this update in the registers or not? So you can see at 26. So this is okay. So this is 31. This side 31 and this is 0. So 31, 30, and 29, 28, 27, and 26. Okay. So 27 and 26. Now this should be set as a double zero as for the input mode. Now this is already set. Okay, this is updated. Why this is updated? Because clock is enabled for this. So clock is enabled for this C mode. We have set this clock enable, and now this is working fine. This mode is working fine, and because of that, our port is not properly set as a mode is not set. So that part will not work. So now we can correct it. And also this is the things we can test register wide value, also everything we can check. We can also check memory address. Okay, so there is memory browser we have. If you want to see some location, what is the value at that location, you can directly check that also. Okay, so GPIO a mode r, so what is the address for this is this one. So you can copy this registers and directly put here and press enter. Okay, so this is coming as a hexadecimal format, so you can check the change the value. So like radix and opposite binary, huh? So you can directly check the value in the memory directly. Okay, instead of registers, all locations are now coming memory. Okay, so this memory location, this value is there, and this is actually a mode register. Okay, so you can check each memory location also what value is set. So that level debugging you can also do. Memory address level, register level you can do, memory address level you can do, and each assembly language instruction level you can check what steps are executing one by one. And so this is just a view you have provided by the QID. Otherwise, print is also a one way to check the value at particular location. Okay, so you can just pass one print statement here in your code, and you can pass any variable name to that, and you can check the value at that time. For that, you have to set perform some setting. So there is one we have already set at the time of debugger. So that was the some SWI. Okay, this is one thing. So you have to open here SWV serial wire viewer. Okay, data console. So when we will open this view, anything which you are printing in the code, okay, so that will be executed in your microcontroller, but that data will be passed to your IDE through this serial wire input. Okay, so you can set this as you have to you have to set some setting for that first time. So if you want to use this as a let me just open again that setting. So let's stop this and again start the debugging. Okay, so debug and that configuration. So you have to set this debugger as a this enable serial wire viewer SWV. You have to enable this. Okay, after that, so you have to open the console when our code will move to the debugger mode. So this will come in the same view, that window and that show view, that SW, this will come here. Okay, so SWV, and here there is option is that SWV IITM data console. So that view you have to open, and here we have to set, first time you have to enable this zero port, okay, to receive the data. So this is just a pin, one register we are using as a getting the data, print data. Okay, what data we are printing in the code, that data will be passed to the that IDE by the microcontroller. So we have to enable this zero pointer. Then okay, after that when you run the code step by step, okay, so you can see now nothing is there in the port. Okay, this output, when we just move one code you can see nothing is there, but when this print statement is executed, so that data as a string will be passed to this pin, and that data will be displayed in your IDE. So this statement is executing on the board hardware. Okay, but output, the print statement output is passing to the IDE, and that is displaying in your this IDE. So you can use this way also for the debugging process. Okay, so you can at the some points where you want to test your code, you can just mention the print statement, pass the variable name, and you can check the value. Okay, so in this way you can also do the debugging. Once we enable this, okay, so this is now enabled. Now you can see the effect. We have to build again. So code is working fine, and that run is this stm32. So again debugging. Okay, so debug is this. Okay, once the clock is enabled, now just move to the same way and see our registers are updated or not. Okay, now we have entered this. Now check the value this time, and you can see the value is updated or not. So previous value was this, so I've been pasting here. Okay, so you can see now this value. Okay, so this corresponding this value is now updated. Okay, as the required data. Previous it was not updated because clock was not enabled for the port A. Now this is updated. So now our we found the error, and we can test like this, we can perform the debugging like this, and we can run our code. Okay, so we can directly if we found the error, we can directly run our code continuously and stop the process, and we can run on our port, like we can directly upload this code on our board, then our code that will work fine. Okay, now our LED is turning on. So in this way, this IDE always provide the way of the debugging. So that things is discussed in the Week-11 also. So in the here presentation, so breakpoint. Okay, so that is the way of the debugging things, and this is uh, how that is per happen actually. So stepping is just is the same thing. So we set some breakpoint, and that is this debugger is also provided by the normal programming language also. C that C what editor we are using, suppose the applet we are using, so that also provides some debugger. You can stop your code, you can check your code step by step. Okay, so Python tutor is also one you can test things where the code is executed step by step. So all things are there. So how actually it is works? So that actually works, Ajay, because how our microcontroller is working, that is executing the operation with the help of these clocks. Okay, so clock is just a continuous cycles, high and low, and for each cycle, some instruction is executing. Some things are happening actually by the microcontroller. So breakpoint is just a handling the clock. Okay, so at some particular point we stop our clock. So that means there is no clock is passing, and so our execution will stop. Our microcontroller execution will be stop at that point. After that we control this clock, so we pass one clock signal, so our one instruction will be execute. Okay, we can just wait for some time, then we can move next clock. So we actually manage these clocks to perform this step by step debugging. And for each steps we can watch, examine registers, memory, or all operation or things to debug the process which is handling by the CPU. So that is the way for the debugging here. So why hardware? Yeah, so this is mostly called as a that software debugging when we are testing our code. So hardware debugging is also important. Sometimes we want to test our hardware, so that microcontroller provides the way to test the debug hardware, to test hardware is working fine for some input or not. So that is, there is one JTAG. Okay, so I have already seen you in the debugger side. So JTAG is also a one way to debug the hardware. So that is full form is Joint Test Action Group, and this is the standard according to the IEEE. So that actually use this type of circuit where each device is connected as a chaining. Okay, chain form, daisy chain. We are saying daisy chain architecture, and some pins are provided. Okay, so the above pin are actually to some manage the things which device we need to check, what condition we want to check for some particular device, so we manage these things from the above device. Here TDI, this is just a input for the device. So here which device we want to check. So suppose we want to check device 2, so we will set our setting from the first two pins, and after that device 1 data. So if we are providing some data into first device, that will be passed directly. But if we are testing device 2, so that will be moved to the each registers of this, what registers are coming inside this device. So that data will be test all the registers, and after that it will return some output. Okay, and that will be passed to the next device. So in this way data will be moved to the all device, and we will check our device the for the every type of input we are getting the correct output, correct expected output or not. Okay, and based on that this is the final output we will get as a TDO, and we will test our device based on this. So this is just a some standard which is defined here as a JTAG, and this is some instruction, and this thing is defined SWD, which we have just discussed now, single wire debug. So that I have already mentioned that how we can use this. So that is the one way. And yeah, this is just a physical connector on the board, because this JTAG and these things, some connections are provided on the microcontroller itself. So this is just a connector on the microcontroller board. You can connect this wire to this microcontroller, and you can pass the value, required value. So this is, you can see this is the pins which I just discussed in the previous diagram. Okay, TMS, TCK, TDI, OTD, this one. And so this is the actual hardware connector, and after that you can pass some data to this pin and check your output, what output should become. So with the help of things you can connect your hardware, you can debug your hardware, it is working fine or not. IDE, so most of the IDE actually perform this connection. So as I mentioned you by the that STM cube ID. Okay, So what ID I am just showing you, that is actually STM ID. So that is directly connecting to the microcontroller debugger. So that is getting some all the data information from the microcontroller to debug. So that provide this debug support by integrating all the things, hardware and software. So this is all about the debugging process on software debug and hardware debug. This is discussed. Next is topic is discuss profiling. So profiling is also a type of debug, but that actually checks. So this is a runtime, okay, runtime behavior. So that debug is also test the runtime behavior, but that actually figure out the only the error, okay, what error is there. But profiling is different things that also check the runtime behavior, but that provides some other information like performance bottleneck, memory resource constraint, scope of improvement. This type of analysis actually it provides. Performance bottleneck means, so suppose if we have one big code, so which part of the code is it taking more time, so what time code is taking, so it is so we can test all this information like how much time is taking of what any code part. Same things, memory, how much memory is using by some our code, that type of information it will be provide. And also scope of improvement, what improvement we can do, because we have some so that efficiency is the main thing. We have the battery limitations, okay, because our code should be fast, should we consume less memory, okay, should we consume less clock cycles uh, to save power or to run for the long time. So we can, our code should be efficient. So because of that, this type of analysis is needed. So here some code is given to, so this is one technique to perform this profiling, that is called as a instrumentation. So that is just actually here we need to add some code in our actual code, okay, original code. That techniques actually add some additional code. Okay, so what type of code that add actually, it's add some start clock. Okay, so this you can see, suppose this is a additional code and end clock. This clock we can directly fetch from this library time.h. This already comes inside the C. So start, that means when we perform this execution, so that will reach the time, okay, for that point. After that, in between, we are performing some operations, and then we will read again the same time end, and after that we will just get the difference between, so end minus start. Okay, so that clock time we are reducing, so end minus start, we will get a consume time by the middle operation, what operation, what time is taken by the middle part of the code, that we will get by this. Okay, start clock and end clock, and finally end minus start. And after that, in the actual value if we want to get, so we can divide by this as a clocks per second. Okay, so we will get some idea that how much time actually some part of the code is taking. So this instrumentation techniques actually added this type of additional code to identify the uh, time by the each part of the code, how much time our code is taking. Okay, so that measurement is performed by this instrumentation techniques. Sampling is the other techniques. So that actually also collect the sample, and that how samples for our program on some particular time, and based on that, it figure out that which less overhead then okay, this is another technique to for the same things. So it collect the sample with the different techniques to identify the same things. But so previous techniques was had some issue, so like that it is adding some additional code in our actual program, so that is actually overhead, okay, for our program also, that will reduce our efficiency of the code. Okay, but this is another technique, so some counter we will use, and on the based on that counter we will identify that how much time our program is taking. So this counter is additionally not by the, we are not adding anything in the code, but we will use some additional counter, and we will identify the duration of our code with the help of this counter. Okay, so this is less overhead, there instrumentation possibility of the missing events. So some event we can miss by this, if we are using this program counter. So this is just a uh, drawback for this. So some tools are there. So gproof is a one tool that is called as a gnu profiler, that perform both type of instrumentation and profiling, both type of things. It provide the call graph, okay, connectivity diagram across function call. So this is tool, and this provides some analysis of our code. Okay, so how function are calling to each other, how many times function is called, so how much time it is our each function is taking. So all type of information actually these tools actually provided. So these are some tools. Same things, this Valgrind is also one debugger tool that also perform this type of instrumentation and all these things, and provide some analysis on the memory and performance, threading, race bugs, this type of issue. So these are some tools that actually provide this type of information of profiling. Okay. So next part. So this is just a summary things, and after that, next part is discussed as a static analysis. So static analysis is about a compile time uh, debugging. We can say that compile time analysis of the code. So when our program is not running on the hardware, okay, so what happened in the embedded system case, we compile our code at the one time. After that, that code actually runs on our hardware for the long time. Okay, so that will continuously run. So this analysis, static analysis, very important. If we can identify the errors at the compile time itself, okay, we can just identify the incorrect things on the compile time itself. So that will not create a problem on the runtime. So how much early we can actually identify the error. So that is just a static analysis, compile time instead of runtime. So that this phase actually check the code, okay, statically without running, and identify all possible errors in the code. So some possible error you can see, so our that this stm cube ide also, okay. If you perform, suppose if you write this code, okay, this code in your program, and when you build the project, that some warning will be provided by the compiler. Okay, so warning, what type of warning will come? So that things, if you have used any variable, if you have created any variable but you not use that variable later, so that type of warning will also be provided by the IDE. So that is actually checking the analyzes the code, analyzing the code, and also checking that your code is properly using all the information which you have declared, all these things, all type of some error which can cause some problem during the runtime, that will be identified, and that will be show you as a warning. So here you can see this is one memory bug. Okay, so here we have mentioned this, we have allocated some memory at the dynamic, this is a runtime call. uh, so but this is, we have not freed it. Okay, so when we are using dynamic memory allocation, we should free the memory, because this if our code is contain this type of things, because our code will continuously run after that. When we will run our code on the hardware, that will continuously run. So at any part where we have allocated some memory at the dynamic memory allocation, by the dynamic memory allocation, and we are not using that later, so that should be free actually. Otherwise that will just consume the memory, and that will provide some this memory. Okay, so that will consume memory without using. So this will be identified by the that static analysis, this part, okay, at the compile time itself. So free is not called. Same memory leak example it is given here. So so same things here, we have declared also, we have also created a variable. For that we have assigned the value, but still we have free. Okay, we missed actually free this, so that is leak things. We are not we have not freed this. And next is buffer overflow. So buffer overflow is just a, we have the size only 5, but we copy the data which have the larger size. So till 5 place, 0 1 2 3 4. Okay, this is the index for this array, character array. So this t h I s and I. this will be stored. But after that 6, 7, 8, 9, 10, this place also, these remaining character will be stored. But this is not actually allocated for us. This part actually not allocated for us, for our program. What part we have allocated? Only this space. Okay, this memory is allocated. So this is actually a overflow things. We are just modifying some memory which is not allocated for us. So that is called a buffer overflow. That type of error will also identified at the compile time analysis. So that's uninitialized variables. Okay, so that this int x, we have not set any value, but we are returning this value to some by our function. So that will create a problem because by default that will contain some garbage value. That will create a problem. So dead code example. So this, okay, so here dead code condition is given and return one, else this will never be executed. Okay, in condition. Huh. Okay, okay. So this type of code you can see because this is a function. So if we are checking any condition, either this return will be executed or this return will be executed. Okay. So if any return is executed, our code is actually stopped at that point. So this print statement will never execute by this. So this is just a additional code which will never execute by any condition. So that is just a wastage code. So that is called as a dead code. And resource management issue, if we are just allocating the memory, uh, we have opened the memory, but we have not closed the memory. O- Open the file, but we not close the file. So that is actually that is also some resource management issue. Potential race condition, so that is based on the thread things. So that is different things. If you know proper operating system things, so that will be the case. So I am also null pointer dereference. So you here you have the null pointer that not contain any address, but you are allocating some value for that. Okay. uh, After free, here you have free the memory, but you are assigning the memory. So that is also a issue. Integer overflow, some max value you have allocated for that, and you are assigning some more value for any variable. Okay, max plus one. So this type of division by zero, this is one issue. So this type of issue that will be identified as the static analyze that level at the compile time itself, not the runtime. Okay, so that type of issue will be identified as a warning. So you can correct your code at the compile time level. That will not create any problem at the runtime. So this is just as a code checker. So some tools are there for this. That C-Lang is there, and this is just one misra guidelines actually, that is called as a motor industry software relatively association, that decided some syntax style actually. Okay, so that code style that is defined to writing the code for the microcontroller, so that become a standard for that. So that define actually rules for the software. Okay, how the code should be write, or that mandatory condition required advisory, all these things that is defined and as a standard. Now this is the example. So suppose if we are writing this type of function, and here one variable is there and then for loop. Okay, so you know that if we have the single line statement inside the for loop, we can write that as a without open bracket and curly bracket. Okay, so that is also one style of the coding. But Mishra guideline actually mention that every that loop and conditional statement should be written with the open bracket and close bracket. Okay, so here the possible error can become like this. Suppose this is here we mention the semicolon. So now this become a single statement, and this x plus equal to I will not come under this. So that is the possibility of the error. So according to the MISRA guidelines, uh, co- every block should be written like this. Okay, if we are writing for loop, we should write block by opening the bracket and close the bracket. So this is the clear guidelines. So that should be followed, and with the help of some code, and that can be checked also. Okay, code is written in proper format or not. So that is the things as a static analysis part. Last thing is discussed is a testing. Okay, so testing is also once our that coding is ready, everything is done on the for the microcontroller. Then testing phases comes. Okay, so this testing phase comes all in the every software development cycle. So testing is what? So means we why should code be tested? Okay, so to check the basic functionality, behavior of the corner case. So already know that in the C programming we have done. If we are writing the solution for code, maybe that code will pass some test case and failing on the some another test case. Okay, so that is just a testing. Your logic is correct for the every situation, so that should be properly checked. So otherwise some corner case behavior will be different for your microcontroller. So that basic for all these things should be checked, how to test code and what part this can be automated. So that is comes under the testing. So first testing is called as a unit test. So that means if our project is big, so that project is generally written as a modular form, that is set of functions. So each function will be considered as a separate unit and will be test separately. Okay, so what input we are providing to the function and what output should we come. So every function will be considered as a separate unit and we will test separately. Okay, so that is called as a unit test. And generally before writing any function we write the test case also. So what is the possible input test case for that, and then we write the code for that and we test them. Okay, so we generally test for the every possible input our function is unit is working correctly or not. So that is comes under as a unit testing. So that should not be after modifying some things, previous testing should not be failed. Okay, so we have already done some testing on our function and we have modified something on that. So previous test case should pass that test case. Okay, that should not be failed for the modification. So that is called as a regression testing. So that is example of code. So so this is the one function. This is the separate function. So what type of input we are reading? The output should be more, uh, should be expected and the correct output. Okay, so that is just tested. Mock function. So this mock function is generally so we generally collect some actually fake data. Okay, as a fake input data, and corresponding we actually test the expected output. So that fake data is actually very close to the real time data. Okay, so what actually what project our task is, why what is the main that goal for our project is, so that will be tested as by the fake real time data. Okay, so we collect some test case and we test our project with the help of this fake data. Okay, with the mock data sometimes you call this. So function pointer, so here same things, mock read temperature, mock set alarm. Okay, so this provides some another data. Okay, so that is like as a fake data that will be provided to the code, and based on that we will check our code what is the behavior. Unit testing is called as a so previous was the unit testing. Okay, so next level is integrating testing. After that we combine our functions and we test as a integrated form. Okay, so once our functions are combined, so what is the behavior after integrating that functions, that is working fine or not, because our total overall project works with the help of different parts of our hardware and codes. So after combining each other, then what is the behavior? Okay, what are the possible input and what is the expected behavior, that is test by integration testing. System testing is overall. Okay, what project we are making, so that once that project is completed, so what is the overall behavior, okay, for the each possible input. So that is system testing. And acceptance testing is just because we are creating this project for some customers. Okay, so what are the expectation we have from the customer or stakeholders, so that all expectations are successfully meets by our project or not, that is called as a acceptance testing. HIL testing. This is also a when our project or embedded system will work with the real time hardware. So that will work perfectly or not. So that is called as a hardware in the loop testing. Okay, so with the all hardware. So we will get some data from another hardware. We will receive the data with hardware, and then we will pass to the another hardware like this. So how our project will work like this. Okay, so that is HIL testing. So yeah, this is the main things and inside the testing. So general guidelines, same things: unit test, real world scenario, multiple test case. All these steps should be performed before using or passing our project to the actual user. Okay, so this is just a like summary things. This is the last thing. So this all things are actually discussed in the Week-11. So what we have discussed now. Okay, so now any query if you have, you can ask. Any question, anyone? So this is the overall summary for the Week-11 things. Okay. Okay, so then you can watch the video lectures. So now, if you haven't watched the Week-11, now the professor have discussed all about the same things which we have discussed today. So now you will get the overall idea of the week content. Okay. So I hope all things are okay. If you have query, you can ask. Otherwise, we can close the session. Okay. Then no query. Then we can close. Okay. Thanks.
Thank you.
Okay.
Thank
Thank.
you, sir.
Bye.